where the green check mark appears. That layer is active. Double-clicking will disable it. A typical noise reduction scheme is to attack the small-scale noise of layer 1 most aggressively with a threshold of 3, tapering down to 2 for layer 2, 1 for layer 3, and 0.5 by layer 4. The amount is up to you. As we strive to acquire sufficient signal, we find an amount reduced from the default of 1 to be appropriate. To combat stronger noise, we recommend increasing the number of iterations before increasing the amount. For now, that's all the settings we need concern ourselves with. While the ATrousWaveletTransform process can isolate the small-scale noise of low-signal regions in individual layers, it's advisable to protect small-scale details of high-signal areas from being smoothed away. For this purpose, we use masks. Recall in Part 1, PI21, when we did the opposite, using either a luminance mask or range mask to protect areas of low signal. We'll now invert those types of masks to protect areas of high signal. Refer back to PI21, PI4, and PI5 to refresh your memory on the art of basic mask making. With areas of low signal revealed for smoothing, we apply ATRU wavelets to the image. While Rogelio prefers to forego smoothing until the nonlinear state, I sometimes apply a modest amount to the background and dim areas of a linear image. Some feel that ATRU handles large-scale noise a bit better than does ACDNR and helps to avoid the dreaded mottled background. Even so, I use just enough to knock the fizz off. PixelMath is a process we've mentioned but have yet to cover. This is as good a time as any to get her done. At this juncture, it's hard to say how essential PixelMath will remain once PixInsight's layers with an opacity setting come online. But for the time being, PixMath is indispensable and something you should know about. While we'll cover it incrementally throughout the series, let's get our feet wet with a bit of simple addition. Despite your best efforts with a particular tool, in this case, ATRU noise reduction, let's say the result is a bit heavy-handed. You can use PixelMath to blend the result with the original image, seasoning it to taste. Let's see how it's done. Rather than making changes directly to an image, you could perform them on a clone. Whichever way you choose, the idea is to add a pre-adjustment version of the image and a post-adjustment version together, thereby reducing the adjustment by half. You can either type in an expression here directly or use the Edit feature. Be advised that the editor has been changed in version 1.8. Here, I copy the image names to save time. And request that 25% of the original image be blended with 75% of the new image. That's it. We'll return to PixelMath for more complex operations later in the series. Next up, nonlinear histogram transformations.